Good morning, good afternoon. Today, we will discuss about the common source field effect transistor amplifier or common source JFET amplifier. To make this circuit, we will need two voltage sources, three capacitors, four resistors, plus one load resistor, and to get the JFET transistor, you will need to type NJF, and we will need the ground. Let's proceed to build the circuit. So here's the diagram of a common source JFET amplifier. We are using the source terminal as common to the input and output. So we will need to label the terminals of the JFET. G for the gate and S for the source and D for the drain. And this will be our V in, so we will also label it V in. And here will be V out. So to set the parameters, this will become our VDD and it will so to set the parameters, this voltage source, we will give it a 16 volts and we will label it as VDD. The second source will become our input and it will have a sine wave with an amplitude of 25 milli and the frequency of 1 kilohertz. The first capacitor will be 0.47 U. The second will be 10 U. And the third will be 40 U. We will call it CS. And these two resistors will be R1, R2, we will give it the values 2 meg and 270K. Now R3 will become RD and it will have 2.4K. And R4 will become RC with 1.5K. RS rather. Now the load resistor will be 10K and it will be labeled R load. And for the JFET, we will just pick 2N3819. In this circuit, the input is applied to the gate terminal. We are using voltage divider biasing, which will bias the transistor in the active region. Therefore, this transistor will work as an amplifier. We are using capacitor C1 and C2. Capacitor C1 couples the input to the gate terminal and capacitor C2 couples the output to the load resistor. We are applying DC voltage VDD to the transistor. The transistor will take the supply and then it will amplify the signal according to the nature of the input waveform. Capacitor CS is connected across resistor RS. This is known as a source bypass capacitor, which bypasses the source current to the ground, and because of that, there is less voltage drop across the source resistor, and it increases the voltage gain at the output. This gate-to-source voltage is reverse biased during the positive half cycle due to the voltage divider biasing of the input signal. To better understand this circuit, it is given that VDS equals VDD minus ID, it's RSRD. So as we know that VDD is always constant, we can see that in this circuit, as the ID increases, the VDD decreases. So as the current is inversely proportional to this voltage. And furthermore, analyzing on that, we will see that in this circuit, for the positive half cycle of the input signal, we will get the amplified negative half at the output. So there is always a 180-degree phase shift between the input and the output. The advantages of JFET, the advantage, the, the advantages of JFET are these devices have the advantage over BJT over having an extremely high input impedance along with the low noise output, making them ideal for use in amplifier circuits that have very small input signals. Also, FETs are less affected by radiation compared to BJT. As for the disadvantages, FETs have a drawback of smaller gain bandwidth product compared to BJT. Faster switching times can be achieved in BJT compared to FET, and performance of FET deteriorates as frequency increases due to the feedback by internal capacitances. Now, we can run this circuit. We just need to type .op to get the parameters. Press run, and we can see the value for VG, VD, VS, ID, IG, IS. So we can list the parameters. Okay, now we have here these values. Now, to see if we obtain the correct values, we can compare it to the theoretical values using voltage divider bias formulas for JFET. So, supposedly for IG, the value is supposed to be 0, and we can see here that IG has a value very close to 0, which is 11.31 nano. And then for the R1, it's supposed to be equals to IR2, IR1 and IR2. We can see that they have the same values. VG can be computed from the formula R2 times VDD over R1 plus R2, and we can get 1.90 volts. And in the simulation, we can see that VG is also 1.90 volts. For the VD, it was computed using VDD minus IDRD, and the result was 10.30 volts. And at the simulation, it's also 10.30 volts. VS is computed by ID times RS, and it also matched the 3.56 volts. Now, for the VGS and VDS, we computed it using these formulas, and we can see that the values using the formulas and the values using the simulation values are the same. So using the formula, we get negative 1.66 volts. And using VG minus VS from here, we also got the same answer. That is also the same for VBS at 6.74 volts. Now to see the simulation results and the waveforms, we have to type that ran from 0 to 10 milli 0. And now when we click on run, you can see the input and the output waveform. You can see that the input and the output waveform is inverted to one another. Using the dot mesh command, we can measure the parameters for the peak-to-peak voltages of the input and the output. Okay, now if we press run and view the SPICE error log, we can see the peak-to-peak of the input and output voltage, and we can compare the two. We can see that the input became a higher value. Now we can also use the dot mesh command to measure the voltage gain, current gain, and the power gain. So dot mesh, transient, AV, parameter VOPP over VIPP. Okay, now that we have input the measure commands for the gains, we can now see them in the SPICE error log after pressing run. And then we can see that the voltage gain is 6.78, the current gain is 161.52, and the power gain was 1.1K. Now, if you want to get the power of the circuit, you can use the formula for power, and we can view it here. So we have power is equal to V times I, and then we can see the waveform for the output power. So we can also use the dot mesh to see the value for power. So dot mesh tran input power TV. Now that we have the measure command for power, after pressing run, we can now view the peak-to-peak value for the power. And you can also see here the average power, which is 1.42. Now, if you want to get the bandwidth, you can get it using the power bandwidth formula. And we need to get the slew rate of the circuit. To get the slew rate, we need to get the slope of the power. to get this to get the slew rate, we need to get the slope of the V out. So to get the slope, we can just press V out twice, and if we set it on 2 points, we can see here that it will yield the slope of the wave. So we can use 1051.08. So 1051.08. Now, to solve for it, will be equals to um, so using the formula, what we got was 493.28 hertz. So that is the power bandwidth of this circuit. So that's it. Thank you for listening.